In this video, we're going to look at the orbitals that were solved by Schrödinger when he applied his equation to the hydrogen atom. So this first picture is of the ground state of the hydrogen atom. Now, chemists use this term ground state to mean lowest energy state. If we go back and think about the Bohr model, that would be the electron in the n=1 orbit, the orbit that's closest to the nucleus. In our shell model, it would be the 1s shell and subshell that we're talking about. So in this case, in quantum mechanics, remember orbitals we have to specify with quantum numbers. So in this case, the lowest energy electron is going to be in the first shell, so n=1. It's going to have a, so since n=1, the only value of the L quantum number that's possible is L=0. And then the only possible m sub L value is also 0. So n=1, L=0, m sub L=0 corresponds to one particular orbital, and that's the picture that we're going to look at. So we would call this the 1s orbital because L=0 means s, and n=1 is referring to the first shell. So this is our first shell and first subshell. So we call it the 1s orbital. So here's some pictures of the result that we get from solving Schrödinger's equation for the 1s orbital. So this first picture here is called a dot plot. And it's a picture that shows you the probability of finding an electron at a particular point in space. So imagine that the electron were like a gnat and we're buzzing around and we were taking little quick snapshots of the gnat. And then we were putting all those snapshots together on one picture, we might get something that looks like this. So where is that gnat most likely to be found? Where's that electron most likely to be found? Or where we have the most spots. So that's going to be here in the middle-ish of the atom. And then you see way out here in this edge of the atom, the spots get fairly thin. So it's fairly rare to see an electron get way out there. So this is called a dot plot. R right here is the distance that we're going out away from the nucleus. The nucleus is the black dot in the middle. So this is another graph of that same picture. It's the probability of an electron being at a point some distance r from the nucleus. So we're just going to say, okay, we're going to go some distance r from the nucleus. What's the chance that the electron is right there at that point, in the area of that point? This symbol right here comes from Schrödinger's equation, is part of the mathematics of Schrödinger's equation, and we don't need to worry about that. We're just going to know that this is the probability of an electron being at a particular point for this particular orbital. And what you see is that the probability is high when the distance from the nucleus is low. That's what our dot plot is telling us. And as we move away from the nucleus, the probability goes down as we move away from the nucleus, right? You're thinking to yourself, hey, this looks nothing like Bohr's model and nothing like the shell model. That electron could be kind of anywhere. I mean, mostly it's here in the nucleus. I thought we said it couldn't be there, and I thought we said it mattered that as you change the distance from the nucleus, its energy changes. Well, it turns out that the 1s orbital has one particular energy, and that electron will has that energy kind of regardless of where it is. So this is kind of weird in terms of physics. We can recover a little bit of the shell model by doing this. Let's imagine that we take this atom and we divide it up into our mind into little spherical shells. So these are kind of like the layers of an onion. So these are kind of like shells. And what we're going to ask is, what is the probability that the electron is somewhere in one of these shells, some distance r from the nucleus? So if I go out a distance r, what's the chance that it's somewhere in this shell that I'm shading in right now? So somewhere in there, what's the probability that it's in there? And these are spherical shells, so even though it looks like a ring on my picture, imagine that this is actually a ball shape. Okay? So that's what's plotted here in this diagram, and it's called a radial probability distribution. So we want the radial probability distribution, which is the total probability of an electron being in one of these spherical shells. And what you see is that the probability is 0 at the nucleus. It goes up and it's peaked pretty sharply right here, and then it falls back down to 0. So this kind of looks like this little point right here, this peak. Well, that's the shell where you are most likely, one of these shells, the little spherical shells here, that's the shell where you are most likely to find the electron. So this is highest probability up here, and then the probability gets lower on either side. And it turns out that this distance from the nucleus is exactly the same distance that Bohr predicted with his model of the hydrogen atom for his first orbit. So that's kind of an interesting relationship there. So this last picture is what we call a contour plot. And a contour plot is a surface, a three-dimensional shape. And what we're trying to do is draw a shape around all these dots so that we encompass like 99% of them. Then we can say that there is a 99% probability that you are inside the surface of this shape. Furthermore, anywhere on the surface of this shape, the probability of finding an electron is equally likely. So you have the same low chance anywhere on this surface. And so for a 1s orbital, what does the shape look like? Well, it looks like a sphere. It looks like a ball. Okay, my little drawing of a sphere looks terrible. But anyway, you get the idea. It looks like a ball, a sphere. So that's the 1s orbital. Now this radial probability idea might have been just a little bit confusing for you. So this is the radial probability distribution of apples falling from a tree. So what we're going to do is draw out some circles on the ground underneath this apple tree, and they're all equally spaced. The distance from one circle to another circle is always the same. And then we're just going to count the number of apples that fall inside each ring. Now as these rings get larger, the area in that circle gets bigger, so there's a bigger chance of having apples there, right? So when you get really close to the tree trunk, these rings are very narrow, and it's unlikely that you'll have apples falling really close to the tree trunk. Then as we get way out here, the area inside these rings is very large, but there aren't very many apples that fall very far away from the tree, and so the probability goes down. So what we see is that right up next to the trunk, you can't get any apples at the tree trunk, and in that little ring around the tree trunk, because it's just such a small ring, there aren't many apples there. But as these rings get bigger, there are more apples, and then eventually as you start moving away from the tree, the number of apples in a ring goes down. At this point right here, at this peak, is going to be the most probable ring to find apples. So if you want to find the most apples, look in that particular ring, which might be this one, let's say. So that's exactly what we're doing with the radial probability distribution function when we're looking at electrons. We're asking, so you're some distance from the nucleus, in what shell are you going to be most likely to find those electrons? What's the probability of finding the electrons in those shells? So it's a good way of kind of reproducing our shell model. So now let's look at some of the other orbitals. So this is the one that we just looked at, n equals 1, L equals 0. And this is that same plot that shows probability as moving away from the nucleus and it falls down. This is a combination both of the dot plot, so the density of dots here in the middle is telling you that the probability is high, and that contour plot. But instead of showing you the whole contour plot, we've chopped out just a section so you can see what's going on inside that surface. So again, it's supposed to look like a sphere. And here's that radial distribution plot. So we just talked about the apple tree, same idea. This is the most probable shell to find an electron in, the most probable distance from a nucleus right there at that value of R. Right, so we can figure out what that is. So next we're moving up to n equals 2, L equals 0. Remember, when L equals 0, our code for that is that it is an S subshell. So this is what we call the 2s orbital. And if we look at the probability of finding an electron some distance r from the nucleus, we see that it starts high right at the nucleus, and then it goes to 0 right at this point, and then it climbs back up, has a peak right here, and then it falls back to 0. In terms of our dot plot, you see that it's really dark blue here in the middle. And then right here in this white region, that's the area where the probability has gone to 0. And then the probability is high again as we move away from that a little bit. And then it falls off and gets really small by the time we get to the edge of this surface. What do you notice about the 1s sphere here compared to the 2s orbital? Well, the sphere is much larger for the 2s. And if we look at the radial probability distribution function, it looks like this. So it has its most probable distance from the nucleus much further than for the 1s, right? So we've moved further away from the nucleus on average. Now there is still a chance, because of quantum mechanics, that the electron could be pretty close to the nucleus, like down here where this little peak is peaked right here. So there's a chance that the electron could be pretty close to the nucleus if it's in the 2s orbital there. But its most likely value is this peak value out here. So this, whatever r value, whatever distance that is, so that looks like about 3 times 10 to the negative 10th meters. So that looks like the most probable distance of an electron in the 2s orbital from the nucleus. Now this region of zero probability is kind of a weird thing, and it has a special name. So we call regions of zero probability, we call those nodes. So a node is just a region, an area in an orbital where the probability is exactly zero. So you'll notice that the 2s orbital has one node, and that node is spherical in shape, right? So it would be a little sphere of zero probability right here in the middle of this sphere. That's the reason that we've chopped this sphere up for you so that you could see the nodes a little bit. Here we look at n equal 3, so we're the n equal 3 shell. L is still 0, so that's still s. So this is a 3s subshell, or a 3s orbital, we would say. And you'll notice that the 3s orbital has two nodes. So as we go up in energy, up in shell number, we're adding nodes. And here's a picture of that. And again, you see that the 3s orbital is bigger still than the 2s orbital. Where's the most probable shell, the most probable distance of finding the electron? Well, it's out here at about 7 times 10 to the minus 10th meters. So where this is peaked. But there's still a respectable chance that it could be about 2 times 10 to the minus 10th meters, and maybe about half times 10 to the negative 10th meters. So right in there. So this is the radial probability distribution plot for the 3s orbital. So now let's look at the 2p orbitals. So 2p orbitals have the n quantum number equal to 2. And remember, if the n quantum number is equal to 2, the L quantum number can either be 0 or 1. So if it's 0, that's an s-type orbital. And we've already talked about those. We talked about the two s's in the last slide. So now L is equal to 1. So this is a p-type orbital. So here's the radial probability distribution plot, and you see that the most probable distance is out here at about 2, a little bit larger than 2. So again, that's kind of consistent with, hey, we've moved out in our shell, and it's kind of similar to the distance that we saw with the 2s orbital. Now, what does the contour plot look like? So we want to draw a shape that's going to encompass like 99% of finding the electron inside that shape. Well, they look like this. So there's a blob, sort of a balloon shape, on one side, and then there's a plane where there's a 0 probability of finding that electron, so that's a node. In fact, it's called a nodal plane, because anywhere on this plane that's drawn here, there's a 0% chance of finding the electron. So there's a really good chance of finding the electron either up here in this lobe or down here in this lobe. Now, if you're thinking about nodes a little closely, you may say, hey, we've just got a single electron in the hydrogen atom. So if it has a good chance of being up here or a good chance of being down here, how does it get from one place to the other without ever passing through the space in between? And it turns out quantum mechanics says you can't answer that question. We can't answer questions about how an electron is moving, like going in space between these two, and where it is. That's something called the Heisenberg uncertainty principle that says you can't know exactly an electron's or a small particle's momentum, how it's moving, and its locations. We can't know both of those with infinite certainty, absolutely certain. And you would sort of need to know that to answer that question about, well, where is it when it's moving between these two lobes? So we leave that as kind of a mystery of quantum mechanics. There's a lot of quantum weirdness that goes on in quantum mechanics, and that's one thing if you're observant and you notice that. Now, we chemists often don't draw these blob shapes exactly like this. We draw them so they look more like lobes of a balloon, but the actual shape looks more like in this picture. All right, so they look sort of like lobes of a balloon. Now, remember we talked about this magnetic quantum number, m sub L. And if L is equal to 1 in this case, m sub L can take on 3 different values, -1, 0, and +1. And that's going to correspond to 3 different orientations. So you'll notice that this particular orbital is oriented so that it's along the z-axis. And so that corresponds to m sub L equal 0. There are 2 other, and since it's along the z-axis, we call it a pz orbital. So there's a little subscript z here. So this would be a 2pz orbital. Now here are the other 2 orbitals corresponding to m sub L equals -1 and m sub L equals +1. Technically, they're just related to those values, but we're going to say that they're equal. So one of these that's aligned along the y-axis is going to be associated with maybe the +1, and this other set of lobes that's aligned along the x-axis here, that's going to be m sub l minus 1. And we call them px, py, if they're along the y or x-axis. So we've got 3 orbitals corresponding to px, pz, and py. And it really doesn't matter which letter we associate with which number up here. So for our purposes, we won't worry about that. Just know that there are 3 different orientations, 3 different orbitals with different regions in space where you will find the electron. Now the shape is the same. The shape is given by the L quantum number, but the orientation is given by the m sub L quantum number. So whether it's along the z, the x, or the y axis. These are the 3 d orbitals. Now here n is going to be equal to 3, and we know that possible values of L are 0, 1, and 2. So we've already looked at 1 and 2, so we're going to look at this one, and when L equals 2, we say that's a d-type orbital. So here's the radial distribution plot. Right here, the peak value, that's our most probable distance from the nucleus, and you see we're moving further out from the nucleus still. And it's pretty similar to the distance a 3s orbital peaks at. So what do these contour plots look like? Well, here's a contour plot for a 3D orbital. And so before, for the p orbitals, we had 2 sort of lobes. Now we've got 4 lobes right here, and they're in these different quadrants in the zy plane. So this orbital has a particular name, just like we talked about the py, the pz, and the px, and this is called dyz. Now for our purposes, we don't need to memorize these names. We just need to know that there are different orientations here. And again, we chemists aren't going to draw these sort of lobe shape. We're going to draw them so that they look more like balloons. So when we're sketching them, we're going to draw them so that they look more like balloons. Now again, if L is equal to 2, there are different values of m sub L. So we start at -2, then -1 is next, then 0, then +1, and then +2. So those are the possible values of m sub L. And you'll notice that there are 5 of them. 1, 2, 3, 4, 5, right? And so that corresponds to these 5 different d orbitals. dyz, dxz, dxy, and this one that's kind of funny has a funny label on it, d sub x squared minus y squared, and this one that's dz squared. Now you'll notice that 4 of them look sort of like a 4-leaf clover, right? They're 4 lobes. This one is a little bit funny shaped, so it looks like 2 balloons, one on the top, one on the bottom on the z-axis, and they're tied together kind of here at the origin. That's where the nucleus would be. And this shape right here, you can think of it as being sort of a squashed donut, and there's actually a hole in the middle, a region of 0 probability right there in the middle at the nucleus. So it's kind of like a squashed donut, and these 2 lobes sort of tied together in the hole of that donut. So you may be asking, what are these XZ, YZ, and so forth labels mean? Well, they do tell us something about the orientation. So like this one, you can see that the lobes lie in the YZ plane, whereas this picture right here, you can see that the 4 lobes lie in the XZ plane. This one is kind of funny, but you see that the main lobes are along the z-axis, so that's there. And here you see that the lobes are along the x and the y-axis. And these actually relate to mathematical functions that come out of solving Schrodinger's equation. So again, I told you it was a mathematical equation, so we have some of these things that are in that mathematical equation. This picture right here shows all 5 of the d orbitals on one plot. And so again, you see that all 5 of them together still have the same spherical symmetry that we think an atom should have. Next, here is one of the possible f orbitals. So in this case, n is equal to 4, and so if n is equal to 4, possible values of L are 0, 1, 2, and 3, and if n is equal to 3, we're going to call that an f-type orbital. Now for f orbitals, m sub L could be -3, -2, -1, 0, +1, +2, and +3. And so there are 1, 2, 3, 4, 5, 6, 7 different orbitals that are f orbitals. And this is one of them. It's called fxyz, and it looks like this. So if you'll remember, our p orbitals had 2 lobes. Our d orbitals had 4 lobes and looked kind of like a flower petal or clover leaf. Gosh, that looks pretty lame, but you get the idea. So we went from 2 lobes to 4 lobes, and now we've got 8 lobes. Yeah, so these pictures get really complicated. You might guess that if we were to look at G orbitals, that they would have 16 lobes. So those pictures get really complicated indeed. So let's look at an energy level diagram. Now we've drawn these already from photoelectron spectrum, but here it is for the hydrogen atom. Now remember, in Bohr's model, our energy level diagram looked like this for Bohr's model. So there was the n equal 1 orbit, that was lowest, and then there was the n equal 2 orbit next, and then 3 orbit was a little bit closer in energy, and then just kept on going up, and they got closer and closer and closer together as we went up. So now we've got something interesting going on. You see that there are many lines here. So each one of these lines corresponds to a different orbital. So for example, this one is the 1s orbital. So for this, n is equal to 1, L is equal to 0, and m sub L is equal to 0. Up here, we have 2p orbitals. You'll remember that there are 3 of them, px, py, and pz. That's what these 3 lines represent. And so for the pz orbital here, this guy, there are 3 quantum numbers that specify that particular orbital. So in this case, n would be equal to 2, that's the shell. L would be equal to 1, that's the subshell. And then we've got this other quantum number that tells us about the orientation. And so m sub L might be 0 in this case, or plus 1 or minus 1. And again, we're not going to be too picky about what label it is. Just know that they're different. So this might correspond to minus 1, this might correspond to 0, and this might correspond to plus 1. So it really doesn't matter what order I write them, but they're just these different values of m sub L. The same thing is going on up here with the 3Ds, right? They're different values of m sub L corresponding to minus 2, minus 1, 0, plus 1, and plus 2. So each one of these different orbitals defines a different region in space where you are likely to find the electron. All these d orbitals, they have that same clover shape, but what's different about them is their orientation in space. So if an electron is here in this particular orbital, you're going to be likely to find it particular places and not other places. So one thing you'll notice about these energy levels is that it agrees with Bohr's model that it is only the shell number that determines the energy. So the 2s's and the 2p's and the 3s's and the 3p's and the 3d's, for example, they all have the same energy. So all of these 3 n equal 3 orbitals, they all have the same energy. When we look at multi-electron atoms, when we have more than one atom in more than one electron in an atom, we'll see that these energy levels split, and that the 2s and the 2p become different in energy. And we saw that in our photoelectron spectra. So we're going to see that happening now with quantum theory actually predicts that.